Okay, I mean, let's just start. I mean, you have seen all these things in the morning session today, right? I think Amri did some things about coding theory. So, since I wasn't there, so what did he teach?
Error correcting and then single bit error corrections and 2-bit error corrections.
Okay.
Hamming distance.
Okay.
Hamming distance based.
So, okay, so how did you do single bit error correction?
So if you have a 5-bit string, then each bit has been repeated twice and then sent it along.
Hmm.
So if there is an error in the single bit, then it is easily identifiable by looking at it because the double is not there.
Okay.
So that is
So,
this
okay,
identification.
so
Correction actually you need to go for 3 bits representation. Same. Each bit has to be represented thrice.
So, did he then go on and show some, what are these code words and what distance between code words and things like
The
that?
distance between code words is defined it as a Hamming distance, a number of ways.
Yeah, that's what I meant.
Yes.
And then, how can you look at this geometrically and things like that?
Geometry.
Like the Hamming ball.
Yeah, that yes.
So then, what is necessary for correcting some errors?
2 or plus 1. It should be 2 or, meaning the length of the code should be greater than or equal to 1. Hamming distance should be greater than or equal to 1.
Okay, so let me just do a quick recap, I guess, so that just to make sure that whatever I want to say, it is. So, coding theory is all about, so you have some message that you want to send to someone else, like you have a satellite which has taken a picture of Mars and then it wants to send that picture back to Earth, right. So, that is a message, or it could be a much shorter message, whatever. So, when you send a message across from from Mars to Earth, or even when your phone is sort of communicating with the phone tower, right. So, there is a lot of interference which destroys a part of the message that you sent, right. So, therefore, I mean, if you just send the message as you have it, it is unlikely that you will be able to actually receive the message completely, right. Or even more dangerously, you would not know what the original message was, right. So, if some critical bits of the message are flipped, the meaning could change completely, right. So, coding theory is about finding ways to deal with this situation. So, what the idea essentially is that you will take the message, right, and as I guess Amri said, that one idea is that you repeat everything maybe 10 times, right. So, then at least if you take the majority of the first 10 bits, then you know the first bit of your original message, something like that, right. So, these are some methods, and in fact, repetition was one of the popular methods that people used to deal with this. Now, I mean, nowadays we use more cleverer and more sophisticated methods, right. So, we are going to talk about one of these things today, like in a more advanced method in this lecture. So, just to recap, so you have this message which has some k bits, or let us just say some k numbers. You will map this message to some set of n numbers, right, and your goal is to somehow figure out how much of this message can you recover this message if a certain number of these code words are lost, right. So, there are many ways of like I guess one of the things that you saw was this. So, if I okay, I have written this like this, that was a bad idea. Let me erase this and just change the notation. So, let me write M1, M2 and so on up to Mk, and this has what was the notation that I used, Z1, Z2, Zn. Right. I did this just so that I mean, I can talk about multiple messages in some sense. So, if you have one message, say M1, this is now a message which consists of like k parts in it, right. For now, let us just think of k numbers. A message is a set of k numbers, a sequence of, well, yeah, k numbers. Now, M1 is mapped to something which I will call Z1, right. Some other message M2 will be mapped to something called Z2 and so on, right. So, potentially your messages could be all possible things of length k, right. So, I can think of my messages, let us say as some vectors in some vector space, right. So, generally speaking, because you have to work with computers, so you cannot work with your underlying field of the vector space to be real numbers, right. So, you fix it to be some finite field, but whatever I am saying mathematically it also works in real numbers, it is just computationally it will not work. So, if I have some field f, so my set of messages is this, right, just a vector space of dimension k over this field f, and think of this as some finite field, or I mean you can think of it as any field, but in when you are working with computers it becomes a finite field. So, I have these are the like this is set of all messages, right. And there is a way, like there is some way we will have which will map these two set of exactly these many code words. Right. So, to keep things really simple, let us just say my field is just F2. So, then I do not have to think about this, then I can think of this as the set of all possible binary strings, right, or you can think of your field as all real numbers as well, I mean mathematically it is fine. Now, yeah, so as you saw in the morning, so there is a notion of this Hamming distance. So, if I take two random like two arbitrary messages in this set of all messages, right, and let us assume that okay, yeah, let us not assume nothing. So, what could you say about the minimum Hamming distance between them? 1, right, which means that if I just send my message directly and one particular bit, one particular among these k things, one of these things is sort of corrupted, then I will get another thing which will also look like a valid message. So, that is the problem, that we do not know which message was sent and which was received, it could be completely something. So, now if I go to the set of code words, I have exactly those many code words, right. So, if my field was F2, then I will have 2 raised to k code words. If my field was some other finite fields like some F9, then it will be some 9 raised to k code words, right. Now, these code words, they are a subset of what? They are a subset of, if I keep the same field essentially f raised to n, right, where n is the message length. So, I am mapping each n is the code word length. So, I am mapping each message to a code word of length n, right. So, I get a bunch of points in the space of all possible code words, right, or the vector space containing all the code words. So, here what would I like for to be able to recover any message that was sent to me, like suppose that I take a message, I convert it to a code word and I send it, right, and you receive something. Now, if what you received, see these code words are a subset of this thing, right. So, they are not a subspace, but just a subset, some arbitrary subset, which means let us say there are a bunch of vectors in this n dimensional vector space, right. So, now you received one of the vectors in this space, and let us say that vector is actually equal to one of the code words, then what is it that you can say like about the message? Well, that would mean simply that either you have received this code word completely uncorrupted, or it was some code word and then it was corrupted in so many places that it changed into another code word, right. So, if you look at the set of messages, if a message changed in only one place, it becomes a new message, but for a code word to change into another code word, it has to be corrupted in many locations. I mean, at least this is the property that we would want, right. It would be really bad if all the code words are also like, you take any code word, there is somewhere you can change it and it becomes another code word. So, what we would like about the space of all code words is that, let us say the Hamming distance of any two code words, let me call them Z I and Z j, is at least something, I don't know, I want to say, let us say some, let me just fix some number, let me call it d naught. D naught is some constant. So, if this is the case, then what can we say, that if I receive a particular code word, then either this code word was sent to me completely uncorrupted, or some other code word was taken and it was corrupted in at least d naught many places, and that is what I received, right. So, to lose information out of a code word that was sent to you, it has to be corrupted in many places. So, it is more resilient to like random noise and corruptions and all these things, right, while you are transmitting it, right. So, this is why these codes are useful essentially. So, now of course, if I somehow started from Z I plus some d naught errors, that becomes a Z j, right. So, this is not helpful, but if we could say that with very high probability the number of errors that I am going to see is say less than d naught minus 1 by 2, right. So, then what is going to happen is that if you have something like this happening, right. So, then when you receive a code word, then you can be certain first of all that if it is actually a code word, right, which is one of those things, then this has definitely not been corrupted. On the other hand, if I receive something which is not a code word, right, because the amount of error I said is upper bounded by this thing because of some whatever external probabilistic reasons or whatever, like that there is not much interference between, let us say, your phone in your pocket and the tower outside, right. But if you go somewhere else where there is a big radio transmission tower or something, then the amount of interference is going to be very high, right. So, when you are in a normal location, then you have some idea about how much error you can expect, like typically, right. And I am saying that typical error is upper bounded by this quantity, right. In that case, if I send a message, some of the symbols of the code word, like if I send a message as a code word, some of the symbols of the code word will be corrupted, but the number of corruptions will be less than this or at most this, right. So, if that happens, then what can I say? Then is there some way I can recover the original message? Right. So, the way I will recover the original message is simply that, well, see, I received something, let me call that y, right, and this y is at distance at most d naught minus 1 by 2 from some code word, right. This is the main property of this y that I received. So, therefore, I should be easily able to basically figure out what the nearest code word to y is, right, and that would be the original code word that was sent to me, right. So, originally somebody sent some code word, it was slightly corrupted, but then I look at this slightly corrupted code word and figure out what is the nearest code word to it, right, because the minimum distance between two code words is at least this d naught and the amount of corruption is less than half of that, there is a unique code word which is nearest to what I received, and therefore, if I can find that unique code word, I am done, right. So, this is the theory behind how coding theory is used in practice, or like this is what we want to do. So, I guess in the morning you saw all these things. So, what I want to do here is look at one particular code word which is sort of built around polynomials and other linear algebra type of stuff. So, this is called Reed-Solomon codes. So, the idea is very simple. So, once again recall that we have this message, right, which is composed of some k numbers that we want to send, right. So, what I do is that I think of these guys as coefficients of some polynomial, which I will write as f of m, right, and this polynomial is expressed like this. It is m1 plus x times m2 plus x square times m3 and so on up to x raised to k minus 1 times m k. So, recall that these messages, they are all part of some vector space with some base field f. Right. So, I can think of this as a polynomial, right, whose coefficients are from that base field, right, and it is a polynomial of degree k minus 1. Now, what is my encoding scheme? Encoding scheme means I have to convert this message into a code word, right. To do that, so I will convert it into a code word with some basically n symbols, right. So, what is the most natural way to do this? The most natural way to do this is to pick some n elements, which I will call, let us say, alpha 1, alpha 2, alpha n in this field, and evaluate the polynomial at those points. So, my code word z 1, so let me just say z m, this m just indicates that it is a code word for the message m. This is simply f m evaluated at alpha 1, z m 2 is f m evaluated at alpha 2, and so on. Z m n is just f m evaluated alpha n, right. So, my code word, that is just this, right. So, if I put this in a bracket like this, is z m 1, z m 2, z m n. So, this is my code word. Sorry?
Like retrieval will not be a problem.
What do you mean by not a problem?
Will be a problem.
Why?
If you don't know what will be the inverse of the exam.
Yeah, we'll come to the retrieval part. For now, I am just describing a code, right. So, I have told you that given if you give me a message, this is the code, this is my encoding scheme. I will think of the message as a polynomial and then evaluate that polynomial at some n points, and naturally like n is much greater than k, right. Well, not much, but like greater than k for sure, depending on how much error correction or whatever you want. So, can someone tell me what is the distance between two code words in this setting?
In that polynomial, you can m of alpha 1 minus alpha.
M of alpha 1 minus,
Meaning the m value corresponding to alpha 1.
see what is the definition of distance between two code words?
Number of
minimum of the difference of value.
Okay, so we will come to minimum later, but let us take two arbitrary code words, right. So, how will you measure the distance?
number of ones.
Right. So, in this case, what are the code words? They are evaluation of a degree k minus 1 polynomial at n points, right. So, therefore, how many points can these two, like if you take two code words which are like this, at how many places can they agree? All places. But look, I said m, let us say you have two different messages m and n prime, for which you have two different code words z and z prime, right. So, can z and z prime agree in all places?
No, at least one place it has to be different.
Is it only one place?
At least one.
Okay, at least one, but can it be precisely one? I mean, why did you say one? That is what I am asking. Why not two?
Maybe two, but
Okay, so here is a fact about degree k minus 1 polynomials. If two degree k minus 1 polynomials evaluate to the same values at k points, then they are the exact same polynomial. Or conversely, two distinct degree k minus 1 polynomials cannot agree on more than k minus 1 points. Right? So if I give you this fact, are you convinced of this fact?
So you mean on all k points, right?
Take two polynomials of degree k minus 1, maximum degree, at most their degree is at most k minus 1. I am saying that if these two polynomials are distinct, then they cannot agree, like if I evaluate them at a bunch of points, then they cannot agree on more than k minus 1 points. If they agree on k points or more than k points, then they are exactly the same polynomial.
That's okay. So,
right?
K minus.
So if I give you this fact, then what can you tell me about the distance of the code words? So if I have two code words for starting from some two distinct messages, then at how many places can these two code words agree?
At least in
K minus 1.
Huh?
K minus 1.
like that.
At most k minus 1. Because if they agree on k things, then they will become the same code. Right? So therefore, if I have evaluated the polynomials at n different points, then at how many places can they be the same? At most
K minus 1.
k minus 1. So at least how many places are they different?
N minus
Yeah.
n plus 1 minus k.
Yeah. So therefore, I can say that distance of RS codes is at least
N plus 1 minus k.
okay. Right? Agreed? So if I use this as my coding scheme to convert a message to a code word, then I seem to get something which has very good distance. Right? Everyone agrees? So did you see something about some bounds in the morning session? Like singleton bound, this and that?
He defined a set called A of n comma d, and then given
Okay.
the bounds
So-
for A of.
Okay, good. So if you go back and look at those bounds that you saw, you'll see that this is this is very close to those bounds, or sort of optimal under those bounds. So this is actually a very, very good code word, right? So the distance of this code word is fairly close to optimal under under the normal setting. Let us say. And the distance, as you can see, it is this much. And as you were saying earlier, right? So if the distance of this code is this much, then if the number of corruptions in a code word is less than what? Less equals n minus k by 2, then there exists unique code word closest to the corrupted code word. So if I encoded my message using this scheme and I sent it from my satellite, and if I receive something, right, and if I am guaranteed because of my external assumptions or whatever that the amount of corruption, amount of messages that were destroyed or manipulated is less equals this number, then whatever I have received, it is not a code word, it could be a code word, it is maybe not a code word, I don't know, but it would not be like it is closest to a unique code word, right? And because of that assumption, the message must have been that unique code word, because if it is some other code word, then the amount of corruptions is more than that number, which will violate my assumption. Right? So when I built my satellite, I made some assumptions about what the weather is going to be like, blah blah blah, other space related things, and based on that I have chosen my n and k. For example, if I was expecting lots of interference, I will choose a very large n so that the distance becomes larger and larger. If I am not expecting a lot of interference, maybe occasionally a little bit, then I can choose maybe n is equal to k plus 5, and that is fine. Right. So, depending on the application or whatever, I will choose n, and that will allow me to decode or or fix errors that I encounter, that destroy my code word up to a certain extent, up to this limit essentially. Right. Now, here is my question to you. Suppose I give you it is guaranteed to you that the number of errors that is going to happen is this, right? And so you know that there is a unique code word that you can find from the corrupted code word. The question is, how do you find it? Can you think of some way? What would be the most simplest naive way? Go over all possible codes. Yes. Yes. I mean, that is the most trivial solution you can do, right? I mean, I have a certain number of code words which is equal to the number of distinct messages. For each message, I will have this unique code word, and I will see what is the distance of this code word from the message that I received, the corrupted message. Right? If it is too far, then naturally that cannot be the message that was originally transmitted. So, I will eventually find a code word which is within that distance from the corrupted message, and that is what I was looking for. Right. So, this is a valid way of decoding a corrupted code word. Right. Unfortunately, as you can see, it takes a lot of time. So, it is not a very good way of doing this. Right. So, originally when people came up with Reed-Solomon code, so if you know a bit of polynomials and linear algebra and all this, you can easily come up with this. What is not easy to come up with is the efficient way of decoding a corrupted Reed-Solomon code. Right. So, the next thing we are going to do is look at an algorithm to do that essentially. Right. So, any questions? क्या नाम है इसका? No, there's a spelling mistake. Right. So, any questions about how we encode RS codes or anything? So, you understand the basics, the basis of it, right? It is, how do you?
So in the previous slide, how do we choose alpha 1, alpha 2, alpha?
Arbitrarily. Yeah. And there are actually in practice there are better ways of choosing this, which will give you some more this thing, but for the purpose of this lecture, this is arbitrary. So, essentially, okay, let me tell you, okay, let me not tell you, but my point is simply that here, as you can see, if you want to decode the corrupted code word to a unique code, right, so then the distance will have to be this, not much you can do about it. But let us say you are sort of your satellite sent a photograph, right, and so even if you do not decode, so your messages are basically a sequence of pixels or something like, or maybe there are different messages or something. So, if at a certain pixel you maybe do not manage to fully decode it, but maybe partially decode it, right, by which I mean that the amount of error that you have is more than this bound, then what is going to happen is that there can be multiple code words which are close to the corrupted code words, right. But even then, by choosing various things cleverly, including these alphas and all that, you can sort of ensure that the number of code words which number of actual code words which led to this corrupted code words, there are multiple of them, but not too many, right. So, instead of unique decoding, you will have so called list decoding with small lists, and that is sufficient. For example, if you are decoding an image, right, if a pixel value is slightly up or down, that does not matter so much. So, things like that. Okay. So, here I think I sort of skipped over one other thing, which is that so this was the message, that was the code word, right. Now, the issue was that when I received something and which is not a code word, I do not know which positions of this received message were corrupted, right. I mean any of the places could be corrupted, I do not know which. But suppose that I knew which, then what could be done? Suppose you knew that like what happened is that this is like corruption essentially, but there is another kind of error that is considered, which is called erasure, right. So, you a message of length n was sent to you, but certain things were erased completely. So, you know that for example, this second thing was completely erased. So, you received the first part and then the third part, right. So, what can you do in this situation? In this situation, how many pieces of the code word do you need to recover the original message? So, recall that fact about polynomials, right. What does it tell you? See, to recover this message, right, what is that message? It is a polynomial of degree k minus 1, right. To uniquely recover this message, how many evaluations of that polynomial do you need? K. You need k, because there are, including the constant, there are k things. So, once you have the evaluation of this polynomial at k distinct points, you can fully recover this, right. So, in your code word, if at least k things survive and maybe n minus k things are erased, you can still fully recover it, right. So, in the sorry,
We will not know which of them is not.
no, that is what I am saying. No, so you were sent a message of length n, but you only received k things. Whatever you received, you are guaranteed that it is correct. Certain other things that you did not receive were erased. Okay,
It's not the
it is not the corruption; it is erasure. So, when your errors are erasure, then you can actually decode, like you can uniquely recover up to a much larger amount of this thing, right. So, I mean you could have tolerated corruptions only up to this limit, but you could tolerate erasures up to double of this, right. So, where can you think of a practical scenario where erasures are natural errors rather than corruptions? Now, I am asking, so corruptions for example show up when you are transmitting a message from a satellite to earth, right. The whatever interference will flip some message or something, but what is a setting where erasures are more natural?
I received few of the message codes and then connection lost.
Okay, I mean that is not exactly this thing, because you are still not guaranteed whatever you received was correct. A better this thing is basically say data centers, right. So, where data is stored, for example Gmail is storing all your emails on their servers, right. So, obviously like at some point some hard disk is going to fail somewhere. So, when a hard disk fails, everything that was stored in that hard disk is erased, and whatever hard disks are working properly, you have the full information there, right. So, in this setting, so Google is not going to store your email on a single hard disk, right, or not going to make multiple copies and store it, because very inefficient. Rather, they will encode your message with a scheme like this and then store it. So, this way if one or two hard disks are lost, they know which pieces of information from the code word were erased, right. So, they can reconstruct the message from the rest of it and then recompute the erased code words and then save that in a new hard disk. So, that is another one setting where instead of corruptions, erasures are happening. Okay, so let us come to this decoding part of Reed Solomon code, right. So, this time we are focusing on corruption errors, not erasures, right. Because in the erasure setting it is sort of easy, right. As long as you have sufficient information, you just need to compute the coefficients of a polynomial out of the values taken by the polynomial at known points. So, here these points these are all known and fixed, everybody knows this. These are like some universal thing that is fixed in advance, right. Everyone knows this, so you do not have to separately send them. Before sending the satellite to space, we fix these things and it is stored, known to both of us. Okay. So, decoding Reed-Solomon codes, it is a somewhat of a clever algorithm. So, this it tries to basically reformulate this problem as solving a linear programming question, essentially sort of solving an LP. Okay. So, let us see how that is done. So, let us say we have some so, let me denote this thing by this number E, okay, to say how many errors we can handle, right. So, whenever I receive a message, the number of errors in that message is at most E. So, then I create a polynomial, okay, E of x, which is defined as okay. So, let me write this first. So, let us say I received something which was z1, z2 up to zn, right. So, here is some z I, right. And how was z1 obtained? It was obtained by taking this polynomial f, well, because for m and evaluating it at alpha 1, right. So, this gave me that, right. F of m at alpha 2 gives me that, f of m at alpha I gives me that, and so on. So, originally this was my message and it was corrupted, right, and then what I received, let me just denote it by y1, y2 up to let us say y n, right. And because there were at most E errors, which means that this set, let us say, like, or let me just say the number of positions where y and z differ is at most E, right. So, let me write down. So, I do not know where they differed, but I know that is at most E. So, let us say that they differ in positions alpha j 1 to alpha j e, right. So, for all these guys, like y j 1 is not equal to z j 1, right. Y j 2 is not equal to z j 2, and so on, right. So, this is not unknown to us. However, we do know that they exist, right. Like maybe the number is not up to j e, but maybe j e minus something, at most these many. So, what I will do is that I will define a new polynomial which I call the error locator polynomial. It is a hypothetical polynomial because we do not know the actual places where it is defined like this simply. It is a product of x is a variable here, okay, x minus alpha j 1 times x minus alpha j 2 and so on up to x minus alpha j e. See, I do not know this polynomial, but I can write down this polynomial hypothetically. Okay. So, in fact, the issue is that the number of errors that can happen is at most E, it is not exactly E, right. So, what I will do is that I will not write it like this, but rather it is written as x minus alpha j 1 times x minus alpha j 2 and so on up to something, right, maybe some x minus alpha j e m, like you have become triple indexes now. So, E m is simply the number of errors that has occurred in this particular transmission, right. So, here E m is less equals E, right, at most E errors. And I want this polynomial to have degree exactly x raised to E. Okay. So, what I will do is that I will multiply it by x raised to E minus E m. Right. So, if I do this, so instead of this it is this, right. So, this polynomial, it has degree exactly E, right, and the leading coefficient of this polynomial is 1. So, this polynomial's coefficients are something that we do not know, like there are some, like the coefficients, there are E coefficients here which are not 1 and they are unknown to us, right. But this is a hypothetical polynomial I can write down given that I received something. Right. So, this is the first polynomial. Now, if I have this polynomial, let us look at the following expression, right. It is fair to say that z I times E evaluated at alpha I is equal to y I times E evaluated at alpha I, right. Why is it fair to say? Because if there was no error at position I in this sent code word, between sent code word and received code word, then z I is equal to y I, right, and E of alpha I mean it is the same thing on both sides. So, therefore, they are the same. Otherwise, alpha, like I was one of the places where they differ, right, but then by construction of this polynomial E of alpha I is 0 on both sides. So, z I and y I are different, but they are multiplied both by zeros. So, again the equation becomes the same, right. So, what I am going to do is, wait, so did I miss something here? Okay. So, I do not have z i's, right, because z I was sent, but I did not receive z I. So, here I will put some other polynomial which I will call q of q of alpha I. Okay. So, more more correctly I should have written, I have this expression q of x times E of x equals to y whatever that is. Sorry?
Index of x.
No, I want to write it in terms of polynomials. So, wait. No, okay. So, I basically have two polynomials, one which I will call q of x, another which I will call, which is E of x, right, and I have this expression that q of, so when you take q of x times E of x, this is equal to y I times E of x when x is equal to alpha I, right. So, this polynomial like q of x is again something that we do not know, right, but what I am going to say is that this is a polynomial of degree at most what is that number should I have, E plus k minus 1. It is again an unknown polynomial. Okay. And here let me actually replace y I should have done that earlier, with f of x. Right. This is what I want. So, f m of x to be more precise. Let me erase this extra box around it. Right. This is this. Yeah, this is what I should have written. Yeah, that is why I was getting confused. So, let us look at this particular expression. Right. let us verify that this expression is true. Right. I mean, I have not specified what q of x is, but it will be a polynomial which will satisfy this property. Right. So, when I set alpha I to be something such that at the ith index z I and y I are the same, that is the code word was not corrupted. In that case, well, first of all, everything will be okay. If the code word was corrupted, then E of x at that point will become 0. Right. So, the decoding algorithm, it relies on two things. First is that once we find q of x and E of x such that q of x is equal to E of x times f of x, then f of x is equal to
ஃபேனை மட்டும் கொஞ்சம் போடுங்க. தலை வலி தாங்கல, என்னவோ பண்ண சொல்லுங்க.
No, sorry, I made a mistake here, I think. Let me fix this. This will become confusing. So, let me instead write this expression that y of I times E of alpha I is equal to f m of alpha I times E of alpha I. And actually my q of alpha I will be exactly equal to this. So, q will be a polynomial which will be equal to the product of these two polynomials. Right. I made a mistake earlier. Right. And if you notice here, when y I is equal to z I, then well, y I is equal to z I and z I is equal to f of m at alpha I. So, then LHS and RHS are the same. And if your code word has an error at alpha I, which is at that point this E of x will become 0 by its definition, because that alpha I will be a root of this E of x. So, therefore, y of I and f m of alpha I, which would be z of I, they are different, but this E is 0. So, therefore, once again this equation is satisfied. Right. And if you look at the right hand side of this expression here, right, then I have defined E of x to be a polynomial of degree at exactly E actually. Right. And this polynomial that you had f of m in Reed-Solomon code, it was a polynomial of degree what? It was a polynomial degree k minus 1. So, the degree of the things on the right hand side, that is equal to exactly E plus k minus 1, right. That is correct. So, q would be a polynomial of this degree, E is a polynomial of degree exactly E, right. So, all we have to do is figure out q x and E x satisfying this condition, this constraint for I from 1 to n. Right. So, once we find such a q x and f of x, because q x is defined like this, f of x, well f m of x would be just dividing q x by E x, and f m x, this was the message we wanted to recover.
So suppose error is 0, it's
Right. So, if error is 0, that is a good question. Let us see. So, what was the definition of E of x? Right. Let me actually move this E of x a little close to where it is supposed to be. So, this is the definition of E of x. So, if error is 0, then the number of alpha j's for which there is error is 0, right, which means that, well, if E of m is the number of errors in this particular message m that I received, E of m is 0, right. So, all these guys here, they will not be there, right, but x raised to e minus e m would be exactly x raised to e. So, once again E of x is a degree e polynomial, it is just that its only root is 0. And so, I think this answer brings up the question that you asked. So, these alphas, I will choose them to be non-zero. 0 will create a problem here for this guy. Okay. Yeah. So, no matter how many errors there are, as long as the number of errors is less equals e, this polynomial, this error polynomial is well defined, and its degree is exactly equal to e. Yeah. Okay. So, question is, how do I find? So, what do we want to do? We want to find q x and E x such that y I times E of alpha I is equal to what? What was the condition? It was equal to q of alpha I. So, what is E of I? It is a degree e polynomial with the leading coefficient being 1, right. It is a, I mean, it is a monic polynomial, that is the name for it. Which means that there are e coefficients in it, right. The coefficient of the first, the highest degree term x raised to e, that is already known to us, it is 1, and there are e other coefficients in it, which can be anything, which we do not know. So, these are unknown. And what about this? So, this was a polynomial of degree k plus e minus 1, right, which means k plus e coefficients, which are also unknown. Therefore, number of unknown is at most, well, let me just write equal to how many? K plus 2e, right. So, if I look at this thing for all I from 1 to n, right, and I have these coefficients of these two polynomials which are unknown to us. So, if I write it down for the first one, what will it be? It will be a linear expression in these unknowns, right. For alpha 1, I will get a linear expression in these k plus 2e unknowns. For alpha 2, I will get another linear expression for this k plus 2e unknowns, and so on, right. So, this gives me what? Let me write here, a collection of n linear constraints, right, on k plus 2e unknowns. And what do we know about E and n? E was less equals k, sorry, n minus k by 2, right. So, which means 2e is less equals n minus k, which means k plus 2e is less equals n. So, I have a system of n linear constraints in at most n unknowns, right, which I can solve. Right. It is just a linear system, as you have seen over the past few days. This is just a LP which you can solve, right, and you can find a feasible solution. That is it. Right. So, there is one more thing which we did not cover, is that I mean there can be multiple solutions to this thing actually, because of various reasons. So, what happens when when that is the case? So, you can prove that in all those cases, the way that we have defined these things, they will always give you the same answer. I think we have run out of time, or maybe gone beyond time, I do not know. No, we are on time. Take it. I mean, I understand that this is a bit of a jump in complexity here, but I hope you appreciate the idea that when first of all we had a very nice encoding scheme, right, using just polynomials, which could take a message of length n and map it to a message of length, sorry, take a message of length k, map it to a message of length n, where the distance is nearly optimal, right. And then we had this very nice algorithm which could recover from like distance by too many errors, right, using just some basic very simple linear algebra and linear constraints. Yeah, so this is all I had to say.
So for a particular receiver and a satellite, the alpha is prefixed for all the time.
Yes.
Then it is very easy for cryptology people to decode the.
See, the purpose of this scheme is not to hide the message, but to recover the message from errors. So, if you want to send some secret message, the very first step would be that you do not send this message, right. So, this is obtained by first encrypting your original message, and then like you send this encrypted message to make it more error resilient, you convert it to a code word and then send. So, those two are different problems. So, any other maybe questions here, anything that was not clear? Well, at least things on this slide should have been clear, hopefully, right, because this was like a specific instance of what you saw in the morning. So, decoding part, this is a bit of a surprising and clever algorithm, but yeah, but the foundation of it is like very simple linear algebra.